Okay, so hello and welcome everyone. Let's get started. So this is week 5 of interactive live sessions for the course on fluid dynamics and turbomachines. It's being offered by NPTEL. This course is being instructed by Professor Shamit Bakshi and Professor Dhiman Chatterjee, both from the Department of Mechanical Engineering at IIT Madras. My name is Debjit. I'm a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together. Now, in the first half of this 8-week course, for the first 4 weeks, we learned about the basics of fluid mechanics. Now, in this second half, we will start to, focus our attention more on the turbo machines and within that also since week 5 is the first week when we really start getting down to it, so a little bit of recapitulation on thermodynamics is also preferred because uh, the knowledge of both fluid mechanics and thermodynamics becomes really important for understanding how turbo machines work and how the designs are made and you know how they operate basically. So without any further ado, let's get started. So here we have the first question of this session, which is asking us that the specific speed of a turbine is defined as the speed of a geometrically similar turbine that would do what? Option A, produce unit power under unit head. Option B, produce maximum efficiency under unit head. Option C, run at unit efficiency and unit head. And option D, operate at maximum power with minimum head. So this question is really related to the definition of a specific speed, and that too for a turbine. So both turbines as well as pumps can have specific speeds, but they are defined in a different way. For a turbine, uh, what is that definition? Is it uh, the speed of a geometrically similar turbine that would, option A, produce unit power under unit head, option B, produce maximum efficiency under unit head, option C, run at unit efficiency and unit head, and option D, operate at maximum power with minimum head. Let's take a look at the solution. It's actually option A, produce unit power under unit head. So, the trick to remembering the definitions of the specific speed for turbines and pumps is to consider what are really, uh, expected of the devices. So, what does a turbine really do? It takes in, so the input to that is head, or the pressure difference, and what we expect out of it is power. So power and head are the important things which show up when we are talking about the specific speed of a turbine. So uh, the specific speed of a turbine can be written as n under root p, where p is the power and h is the head available for the turbine. Now, similarly, for a pump, not I shouldn't really say similarly because the things are not similar, which is what is challenging. So, what does a turbine really do? A turbine takes in head as input and gives out power as output. So that is why these two things show up in the formula for specific head, as well as it's defined as, what would be the speed of a geometrically scaled up or scaled down turbine which would be able to operate at unit head and produce unit power. Now, for a pump, what are the uh, important features of a pump? A pump should also, a pump should be able to operate a certain flow rate which is applied to the pump, and what it gives is that it increases the pressure of the fluid which is flowing at that given flow rate. So uh, once again, it's the head which is increased by the pump. So once again, so similarly, for in the formula of uh, the specific speed for a pump, it would show up as N into under root Q, which is the flow rate, and we have head in the denominator. So, and what would then the definition be? Then the definition of a specific speed for a pump would be that it is the speed of a geometrically similar pump which handles one unit flow rate of volume flow rate of fluid and produces one unit head. Right. So it's really tied to the actual practical use of these turbines and pumps. All right. So that is why the answer to this question would be option A, that the specific speed of a turbine is defined as the speed of a geometrically similar turbine that would produce unit power under unit head. All right. So let's move along. We'll move on to question number 2 now, which is a simple one. So it's asking which type of a pump is which type of a pump is most suitable for high flow rates and low head applications. High flow rates and low head applications. Is it option A, axial flow pump, option B, radial flow pump, option C, mixed flow pump, or is it option D, a screw pump? So high flow rates, that is Q is high and head is low. So you can imagine, the specific speed for this application would also be very high. So what type of a design of a pump makes it more suitable for such an application where the flow rate is very high, but the head to be produced or the pressure difference to be produced by the pump is not that high, it's low? Is it option A, an axial flow pump? Is it option B, a radial flow pump? Option C, a mixed flow pump? Or is it option D, a screw pump? So here's question number 2 of today's session. Um, it's asking us which type of a pump is most suitable for high flow rates and low head applications. Is it option A, axial flow pump? Is it option B, radial flow pump? Is it option C, mixed flow pump? Or is it option D, a screw pump? Okay, so let's take a look at the solution. It's actually option A, an axial flow pump where the bulk flow rate is actually um, in the same direction as the axis of the runner. So if this is the runner, then the main flow direction would be along the axis of it. So not strictly, but you can think of this as a fan, right? Now the thing is, this type of a design makes it the most suitable for a very high flow rate. As you can see, the entire projected area of the turbine, uh, of the sorry, not turbine, of the runner of the pump is perpendicular to the direction of the flow rate, so it can handle the uh, entire uh, direction. Sorry. One second. What's this? Okay. The moment. Reshare my screen in this screen only. Now if I open picture, yeah, it's properly visible. Yeah. Okay, sorry about that technical glitch. Anyway, so as I was saying, so for an axial flow pump, the flow direction or the entire flow area is perfectly overlaps with the projected area of the runner. So that's why it can handle a high flow rate. But the downside to it is that it's very difficult to produce a very high pressure difference using this configuration because there's no centrifugal acceleration component acting there, which is uh, more dominant in radial and mixed flow pumps. So another important piece of distinction here is that, sorry, is that these three are you know continuous flow devices, whereas the screw pump, this is a positive displacement device. Positive displacement pumps are what? They are uh, they are pumps where the fluid is always covered by some physical barrier. So be it reciprocating pumps or gear pumps or screw pumps, there you can produce a very high uh, pressure difference because there's a solid boundary always moving that is driving the fluid from a low pressure to a higher pressure, uh, uh, from a low pressure to a higher pressure. So it really ensures that the fluid goes without any sort of leakage. But the downside to that, there are two downsides. One is that it's impossible, almost impossible, to get a continuous flow rate using positive displacement devices because there are you know a fluid, imagine getting surrounded by some solid and then being transferred, and that whole process would be discontinuous. There will be one block of fluid transferred, then the next block comes in, like that. So that's the, and also uh, average flow rate which we can achieve is not that high for positive displacement bounds. Whereas for continuous devices, they can ensure a continuous flow rate as well as, uh, but one disadvantage is they can produce pretty high heads, but one disadvantage is that it cannot ensure that 100% of the flow will go through without any leakage losses. Okay, so let's move along. We'll move on to question number 3 now, which is asking us that uh, what is dimensional analysis used for uh, when it comes to turbo machines? Is it to primarily do what? Is it option A, to calculate energy losses? Option B, to derive similarity relations and scale models? Option C, to measure the risk of cavitation? Or is it option D, to determine blade stresses? Which are the stress components acting on the blades of a turbine? So what is dimensional analysis used for when it comes to turbo machinery? Is it to option A, calculate energy losses? Is it to option B, derive similarity relations and scale models? Is it option C, to measure cavitation risk? Or is it option D, to determine blade stress? Okay, so here's question 3 of today's session, which is asking us what is dimensional analysis used for in turbomachinery, in the study of turbomachinery. Is it to option A, calculate energy losses? Is it option B, to derive the similarity relations and scale models? Is it to option C, measure cavitation risk? Or is it option D, to determine blade stress? Let's take a look at the solution. It's actually option B, to derive similarity relations and scale models. So basically what dimensional analysis helps us do is that it lets us get rid of all dimensional uh, physical quantities, or we become less focused on the exact number of each and every parameter in play, which could be many, and instead we focus on a smaller set of numbers, which are the dimensionless groups which come up, and they are the ones who really encapsulate the physics of any problem, and particularly in turbo machinery. And then what that lets us do is that it helps us, uh, to compare similar results, you know, to really find the similarities between different results. So let's say I'm using a big pump with a high flow rate and some high head. I can compress it down to a smaller pump operating at lower flow rates and lower producing lower heads, and still, if the physics is the same, I can do experiments with it, run numerical simulations on it, and still arrive at some meaningful conclusions. So this is what scale models are. So you can either scale up or scale down uh, the actual design that you're aiming for, and then that will help you to make proper assessment of the design and possibly improve it. So that is why dimensional analysis is a very useful tool. Also, another important aspect is that it really reduces the number of parameters you're playing with. So let's say you have seven different variables and you want uh, 10 different values for each of those numbers, then what you're looking at is 10 power 7 experiments. Really, the combinations are 10 power 7. Whereas if you can boil it down to, let's say, three or four uh, non-dimensional groups, then all you're looking at is 10 power 3 or 10 power 4 such experiments. To give you the exact same knowledge, by the way, you arrive at the same conclusion, but in a much more smaller as well as, I think, more meaningful way. You really understand the physics better when you're operating in the non-dimensional regime as compared to the dimensional one. So it's really a very powerful tool, has a lot of benefits attached to it, and which is why it's heavily used in the field of turbo machineries. Okay, so that was question number 3. Let's move on. We will move on to question number 4 now, which is asking us that for a turbine, the power delivered to the runner divided by the water power supplied to the turbine inlet is called what? Is it option A, mechanical efficiency? Is it option B, hydraulic efficiency? Is it option C, overall efficiency? Or is it option D, volumetric efficiency? So for a turbine, the the power delivered to the runner divided by the water power supplied to the turbine inlet is called what? So this is the ratio of these two powers. So power delivered to the runner divided by the water power supplied to the turbine inlet is called what? Is it mechanical efficiency? Is it hydraulic efficiency? Is it overall efficiency? Or is it option D, volumetric efficiency? So let's take a look at the solution. It's actually option B, hydraulic efficiency. So, uh, you know, there are obviously different efficiencies involved. The hydraulic efficiency is the first sort of first efficiency, which talks about the first loss as such that goes on, that from the turbine inlet to the runner, there is a loss of the power carried by the water or any other fluid for that matter, and that's the hydraulic efficiency. Then next comes, the actual cycle efficiency of the turbine, how much power it can extract from whatever power was supplied to it at its runner. Then comes the mechanical efficiency. So, there are frictional losses in the shafts of the turbine to the power delivery. Uh, so usually turbines are connected to uh, you know, some turbine shaft will be connected to some electromagnetic coil, which would uh, rotate and then produce electricity. So before that, uh, due to frictional losses in the shafts itself, shafts and bearings, there's a mechanical efficiency involved there. And also volumetric efficiency is like uh, for continuous flow turbines, uh, there is always some leakages, the leakage of water or the working fluid. So that's the volumetric efficiency. So the entire volume that you supply is not what is used up. So, and everything all together gives you the overall efficiency of the turbine. Okay. So let's move on. We'll move on to question number 5 now, which is asking us which option correctly ranks the typical specific speed ranges for Pelton, Francis, and Kaplan turbines in increasing order. So you can see greater than given here. So, or sorry, less than signs used here to mention that, just to showcase that the next item has a higher specific speed compared to the previous one. So the orders given in the options are option A, Kaplan turbine less than Francis turbine less than Pelton turbine. Option B says Pelton less than Francis less than Kaplan turbine. Option C says Francis turbine has a lower specific speed than Pelton turbine, which has even lower specific speed than the Kaplan turbine. Then option D says it's the order B is Francis turbine less than Kaplan turbine less than Pelton turbine. So you really have to find out what are the typical specific speed ranges for each of these four designs of turbines, and then arrange them in an increasing order, meaning the smallest one first and the largest one last. Okay, so let's take a look at the solution. It's actually option B, Pelton greater than Francis greater than Kaplan turbine. So once again, we have to remind ourselves what the specific speed for a turbine is, and that is given by N under root P H power 5 by 4. Now, uh, okay. Now let's consider the designs of these turbines. So Pelton turbine is really uh, uh, what is known as a impulse flow turbine. So basically, it's like a water wheel. So I'll just draw one blade where water comes in and falls, and this basically rotates the runner. So there are multiple blades attached to it, and there could be more than one jet also coming and impinging on it. So depending on how you uh, design the flow of water around it, as well as the blade spacing. So these are also known as buckets. So the bucket spacing would determine how many such buckets do you have. So this is what the Pelton turbine looks like. Now Francis turbine is a bit mixed. So it has one impulse component as well as a reaction component. So it's a mixture of both impulse plus reaction. Whereas a Kaplan turbine, so Pelton is impulse alone, and a Kaplan turbine is entirely reaction. So as a result, what happens is that the head requirements are very different. So for impulse turbines, the head requirement is huge, whereas for reaction turbines, it can operate efficiently even under low heads. And as far as flow rates are considered, the flow rates would be lowest for the impulse turbine, and it would increase as the uh, rate of the proportion of reaction versus impulse increases, and is the maximum for the reaction turbines. So if we look at head, which appears in the specific speed here in the denominator, so as head keeps getting lower and lower, the specific speed would keep getting higher and higher. As a result, the correct order would be Pelton first, then Francis, then Kaplan, because the Kaplan turbines can operate at the lowest head available. So the correct order in terms of an increasing order of uh, the typical specific speeds at which these turbines operate is Pelton less than Francis less than Kaplan. All right. Now moving on, we'll move on to question number 6 now, which says that there's a pump which develops a head of 20 meters and delivers a 0.08 meter cube per second flow rate at uh, 1200 RPM. What is the specific speed of this turbine? And also, the formula is given in the question. So you just plug in the numbers and find out what it is. Okay, so let's take a look at the solution. It's option B, 52. Let's see how we can get there. So the specific speed of a pump is given by n square root of q and 3/4 of the head h. Let's just plug in our numbers. So we have 1200 RPM into flow rate cubes of 0.08 and h power 3/4. So the h is 20 power 3/4. I'll need to use a calculator here. Give me a second. So first of all, the square root of 0.08 is 0.2828 multiplied by 1200 gives us 340 divided by, now here's the tricky part, so 20 power 3/4, that's 0.75. Mm, makes sense. So it's okay. Sorry, the number is coming out to be 35.88, or closer to 36. So 152 is not the right answer. So in fact, none of these are the right answer given here. So it should really be 36. Sorry about that. Okay, but pretty straightforward. Let's move along. We'll move on to question number 7, which is asking us that for a geometrically similar pump, if the diameter and speed are halved, then the flow rate changes by what? So a geometrically similar pump, this is an important point. And in that, if you halve the diameter as well as the speed, what happens to the flow rate? So diameter is d, speed is n, flow rate is q. What happens to the flow rate? Does it become, option A also gets half, option B it gets quartered, option C it becomes 1/8, or is it option D it becomes 1/16? So once again you have to use similarity laws and find out what happens to a geometrically similar pump, which if you halve the diameter, so basically you're decreasing the whole size of the pump to its half, and also you're decreasing its speed. If you do that, what happens to its flow rate that it can handle? Okay, so let's take a look at the solution. It's 1/16. So this is what basically happens. So according to similarity law, so one of the non-dimensional groups that we get is called a flow coefficient, which is q over n dq. Now we have, uh, you know, uh, we basically have two pumps over here, one model, one prototype. So let's call them 1 and 2. So q1 by n1 d1 square, d1 cube, sorry, and q2 should be equal to q2 n2 d2 cube. Now, why do they have to be equal? Because it's a geometrically similar pump. Now, we just plug in the values after a bit of rearrangement. So we are looking at the flow rate. What happens to the flow rate? So it's q2 over q1. That should be equal to n2 d2 cubed over n1 d1 cubed. Now we halved these quantities. So, d2 is basically half of d1, and n2 is also half of n1. N2 is half of, yeah. So this is 1 half due to the n2 over n1, and for d2 over d1 it is half cubed. So as a result you get 1 by 2 power 4, which is 16. So the flow rate becomes 1/16 of its original value. That gives us option D, 1 over 16. Okay, so let's go to question number 8 now, which is a numerical type question. Now, what is it telling us? It's telling us that there's an axial flow compressor in a jet engine which receives air at a stagnation pressure of 100 kilopascals and a stagnation temperature of 300 Kelvin. Then what happens is that the compressor then compresses the air and increases its pressure. So it delivers air at a total pressure of 600 kilopascals. So and also the information that's given to us is that the total to total isentropic efficiency of this compressor is 0.85 or 85%. Now, the specific heat at constant pressure for air is given, and also the ratio of specific heats gamma is given. What you have to find is what is the exit total temperature and also the power required to compress a mass flow rate of 12 kg per second. Since it's a compressor, you have to find out what the uh, you know power requirement of to run the compressor would be. So, since it's an isentropic process of compression, uh, let's find out what the ideal uh, stagnation temperature would be if it was isentropic. So T over 0 to T0 to S over T01, you can say S, but really they are the same, T01 and T01S. This is given by P02 by P01 to the power gamma minus 1 over gamma. This is for an isentropic process. Now, what values do we know? So T0 to S is what we are trying to find out. Should be equal to T01S, which is 300 kelvins, and the pressure ratio is 600 by 100. So it's basically 6. So I'll just write 6 over here if you don't mind. So it's 6 to the power gamma minus 1 by gamma. So that's 0.4 by 1.4. I'll need a calculator here. Let's do this. So zero point 0.4 divided by 1.4 is 0.2857. This is an important number for air, which you can remember. But then again, like for all materials, there are lookup tables. So remembering isn't really that great an idea. Now, what we need to do is 300, no, sorry, 6 power this. 6 power 0.2857 is 1.668, and we multiply that by 300. So that gives us something like 500 point something. For simplicity's sake, we'll just say it's 500 Kelvin. Now, this is what the stagnation temperature would have been if the process was isentropic. Now, since it's not, there is a certain efficiency attached to it. So, you know, the total to total efficiency is defined in this way. that the actual T02 minus T01 over the isentropic T02S by T01 or T01S, they don't really matter. They're basically the same thing. So from this relation, we can find out T02, which is T01 plus this efficiency. Let me move this over here. Okay, so we have total to total efficiency multiplied by the isentropic stagnation temperature minus the inlet temperature. So T01, as we know, was 300 plus 85%, that's the efficiency, and the temperature that we computed was 500. So 500 minus 300. So this is basically, let me do this math myself. So this is 200, 200 into 0.85. So that's double of 85, which is 170. So 170 plus 300 gives me 470. So that's the first part, the actual exit temperature. Now, what is the power required to compress it? The power requirement P would be equal to the mass flow rate into Cp into delta T. Cp is also given, delta T we can find from here, we know 470, yeah. So the mass flow rate is 12 kgs per second into Cp is 1005 joules per kg Kelvin into the temperature difference, which is 470 minus 300, which is 170. So it's a simple multiplication now. So 170 into 12 into 1005. So that's 2 point something megawatts. It's basically 2050200. Yeah. So this should be in watts. So 2 point something megawatt. I'll just you know round it to 2 megawatts. Something like 2 into 10 power 6 watts. Okay, so let's keep rolling. We'll move on to question number 9 now, which is asking us that a gas turbine receives combustion gases at a total pressure P01 at 1.8 megapascals. The total temperature T01 is 1500 Kelvin and it expands to a total pressure of 0.2 megapascals. The total to total efficiency of the turbine is given at 90%. Once again, the Cp value as well as the gamma value for the combustion gases are given, which if you notice are very similar to air but not exactly same. And also the mass flow rate is also given, that's 10 kgs per second. Okay, so similar process, let's do this. So what we need to find is the isentropic temperature first that it expands to. So T02S over T01 should be equal to P02 by P01 powers gamma minus 1 by gamma. So T02S is T01, which is 1500 Kelvin. It's at a high temperature, and the pressure ratio is zero point 0.2 over 1.8, both in megapascals, so that cancels out. And gamma is 1.33, so this is 0.33 divided by 1.33. Let's do the math. So it's 0.2 divided by 1.8 power 0.33 divided by 1.33. This gives me something like 0.579 Let's multiply this by 1500. That gives me 869.6. I'll round that off to 870. I'll round that off to 870 kelvins. So this is the first part, the isentropic exit total temperature. Now the next part is to find the actual exit temperature. So once again, we know that the total to total efficiency is uh, T01 minus T02S for a turbine. No, this is just T02 and T01 minus T02S, which is the isentropic process. So here T02 is basically T01 minus this efficiency into the temperature difference here. T01 is 1500, this efficiency is 90%, and this difference is 1500 minus 870. So again, let's do the math. So 1500 minus 870 gives me 630. I multiply that by 90%, which gives me 567. And this has to be subtracted from 1500. So that gives us 933. So this is the actual exit temperature. So this is B, this is answer A, and finally the actual power produced by the turbine. So once again, the power produced would be m dot Cp into actual delta T. So m dot is 10 kgs per second, Cp is given as 1150, and the actual temperature difference is 1500 minus 933, which is the actual exit temperature. And this would give us, see, 933, sorry, 1500 minus 933 is 567, multiplied by 1150, multiplied by 10. So once again, that gives us a big number, which is 6.5 something. Where's my cursor? Sorry. So this is 6.52 10 power 6 watts. So basically 6.52 megawatts. This is answer C. So as you see, the process is very similar, just applied to different contexts. Now let's take a look at the last question of today's session, which is also, similar. It's asking us that a centrifugal compressor receives air at a certain pressure, which is 100 kilopascals, as well as temperature 290 Kelvin, and delivers it at a pressure of 500 kilopascals. Once again, the total to total efficiency is given, and the properties are given, and mass flow rate is given. So it's very exactly similar to question number 8. So let's just go through the process. So T02S by T01 is P02 by P01 powers gamma minus 1 by gamma. T02S should be T01. I'll just plug in numbers here. So T01 is 290 Kelvin, and the pressure ratio is 5 because it's 500 divided by 100. So 5 powers, once again, gamma is 1.4. So 0.4 by 1.4 we can try to remember is 0.2857 something. So this really gives us 5 powers 0.2857 is 1.58 multiplied by 290. It's something like 459 point something. I'll round it off to 460. So this is the ideal or isentropic uh, temperature, uh, exit temperature. The question is, what is the total isentropic total temperature rise? So that rise would be T0 to S. So I'll call this delta Ts minus T01, which is 460 minus 290. That is 106170 Kelvin. So this is the answer to the first part. Now the next part is the work input required. So okay, so first of all, the actual temperature difference has to be found out. And as we saw earlier, the actual temperature is this plus the efficiency total to total multiplied by the ideal temperature difference. So that's 290. The efficiency is 80%, and the uh, isentropic total temperature rise is 170 Kelvin. So let's do this. 117.8 is 136 plus 290. That gives me 426. And the work input is again m dot Cp actual total temperature difference. So the mass flow rate is 5 kg per second. Cp is 1005 for air, and the actual temperature difference is zero point 0.8 into 170, which we found to be 136. So if we simply do the math, 136 into 1005 into 5, that gives me 683. Okay. So once again, I'll just round things off here. So it's 6.83 into 10 power 5 watts. So we can call this 683 kilowatts. So that's answer B. Okay, so that was the last question of today's session. Thank you. So we will meet again next week at 3 o'clock.